Welcome back to G Fun Facts Online. Today, we are going to talk about a revolution in physics. And when I say revolution, you probably imagine the Large Hadron Collider in Europe, a 27-kilometer ring smashing atoms together at the speed of light. Or perhaps you imagine the James Webb Telescope peering back into the cosmic dawn. These are the machines we associate with big science. But in 2018, the scientific world was completely upended by something so simple. It sounds like a high school science project. The tools involved were a piece of Scotch tape, a few flakes of carbon, and a literal twist. This is the story of Twistronics, a new discipline of physics that asks a deceptively simple question. What happens when the geometry of a material becomes as important as its chemistry? To understand this, we have to look at the material that started it all, graphene. You have likely heard of graphene. It was isolated in 2004 by Andrei Geim and Konstantin Novoselov, a discovery that earned them the Nobel Prize. Graphene is, simply put, a single layer of carbon atoms arranged in a hexagonal honeycomb lattice. It is a wonder material for many reasons, but for physicists, it is famous for its speed. Graphene is a semi-metal. In a standard conductor like the copper wiring in your house, electrons are constantly bumping into atoms and into each other. That bumping creates resistance, which is why your laptop charger gets hot. But in graphene, electrons behave as if they have no mass. They behave like Dirac fermions, zipping through the carbon lattice at 1/300th the speed of light. They are exceptionally fast. And that is actually a problem if you are looking for exotic quantum states. Think of the electrons in graphene like commuters on a high-speed train. They are moving so fast, focused entirely on their destination, that they ignore their fellow passengers. They do not interact. But for superconductivity to occur, that holy grail state where electricity flows with zero resistance, you need the exact opposite behavior. You need electrons to talk to each other. In conventional superconductors, electrons form what are called Cooper pairs. These are pairs of negatively charged particles that normally repel each other, but under specific conditions, they bind together and flow in unison, like a superfluid. For years, theorists believed that the only way to get graphene to superconduct was to chemically dope it, essentially forcing foreign atoms into the lattice to change its properties, or to crush it under immense pressure. The electrons were just too fast to pair up on their own. But in 2011, a theorist named Alan McDonald at the University of Texas at Austin, along with his researcher Rafi Bistritzer, proposed a different idea. They published a paper that, quite frankly, most of the mainstream community ignored. They calculated what would happen if you took two sheets of graphene, laid one on top of the other, and rotated them. They predicted that at a very specific angle, around 1.1 degrees, something strange would happen to the electronic structure. They predicted that the massive speed of the graphene electrons would vanish. In physics terms, they said the Dirac cones, the graphs used to map electron energy and momentum, would flatten out. This creates what is called a flat band. Now this is a crucial concept to grasp. When an electronic band becomes flat, the kinetic energy of the electrons drops to zero. The electrons stop zooming around. Using our train analogy, the high-speed train has stopped. The commuters get off and are suddenly forced into a crowded room. Because they are no longer dominating the scene with their speed, they are forced to interact with one another. The dominance of kinetic energy is replaced by the dominance of Coulomb interactions, the repulsion between negative charges. McDonald and Bistritzer predicted that this magic angle of 1.1 degrees would be a playground for correlated physics. But here was the catch. The engineering challenge was considered impossible. If you were off by just 0.1 degrees, the magic would disappear. The electrons would keep moving, and you would just have boring old graphite. For 7 years, this remained largely a theory, until a team at MIT, led by Pablo Harrio Herrero, and a graduate student named Yuan Cao, figured out how to do the impossible. They didn't use a $1 million nanofabrication machine. They used a technique called tear and stack. This relies on a clever bit of manual dexterity. If you take two different flakes of graphene from two different crystals, you can never be sure how their atomic lattices are oriented. You don't know where 0 degrees is. So the MIT team didn't use two flakes. They used one. They started with a single pristine flake of graphene on a substrate. Using a sticky polymer slide, they picked up only half of the flake. The graphene tore, leaving half on the bottom and half on the sticky slide. Because these two pieces came from the same crystal, their atoms were perfectly aligned. Then, they simply rotated the stage holding the bottom piece by exactly 1.1 degrees and lowered the top piece back down. This created twisted bilayer graphene. When you look at this structure through a scanning tunneling microscope, you don't just see carbon atoms. You see a moire pattern. You have probably seen a moire pattern in real life. If you look through two screen doors that are slightly overlapping, or two layers of sheer fabric, you see a new, larger, shimmering pattern emerge. In twisted graphene, The two hexagonal atomic lattices interfere to create a massive superlattice. While the distance between carbon atoms is tiny, about 0.14 nanometers, the moire superlattice at the magic angle has a periodicity of about 13 nanometers. This larger pattern acts as a trap. It creates a landscape of energy valleys that locks the electrons in place. The tunneling energy between the layers exactly cancels out the kinetic energy within the layers. The electrons are trapped in the moire cells, unable to escape, and forced to interact. In March 2018, the MIT team dropped 2 papers in the journal Nature that shocked the world. The first paper showed that this magic angle twisted bilayer graphene could become a Mott insulator. This is a state where electrons are stuck in place, not because there is no path for them to flow, but because the traffic jam is so intense. They are repelling each other so strongly that everything gridlocks. The second paper was the bombshell. By applying a tiny gate voltage, essentially a small electric field that adds just a few extra electrons to the system, the material transformed from an insulator into a superconductor. It conducted electricity with zero resistance. Now the critical temperature was very low, about 1.17 Kelvin. That is extremely cold, but what mattered was the density. Standard superconductors need billions of times more electrons to carry the current. This magic angle graphene was superconducting with a skeleton crew of charge carriers. This suggested that the mechanism behind this superconductivity was something new. It looked suspiciously like the mechanism found in cuprates, those mysterious copper oxide ceramics that hold the record for high-temperature superconductivity. Suddenly, graphene wasn't just a material, it was a Rosetta Stone. Physicists realized that if they could solve the puzzle of twisted graphene, they might unlock the secrets of room-temperature superconductivity. This discovery birthed the field of Twistronics. It represents a fundamental shift in how we engineer matter. For the last century, we have modified materials by changing their chemical composition. We dope silicon with phosphorus to make transistors. We alloy steel with chromium to prevent rust. Twistronics suggests that we can change a material's destiny simply by rotating it. Since 2018, we have discovered a zoo of phases in this material. If you plot the behavior on a graph, you get a complex phase diagram. You have the superconducting dome, where resistance vanishes. You have the Mott insulator state. And above the superconducting temperature, you have a strange metal phase, where resistance scales linearly with temperature, a behavior that defies standard quantum theory. But the magic didn't stop at superconductivity. Researchers found that at certain alignments, twisted graphene exhibits orbital ferromagnetism. In a standard magnet, like the one on your fridge, magnetism comes from the spin of electrons. In twisted graphene, the magnetism comes from the orbital motion of electrons swirling around those moire cells. They create tiny current loops, effectively turning the material into a grid of microscopic electromagnets. This leads to the Quantum Anomalous Hall Effect, where electricity flows along the edges of the material with zero resistance and zero magnetic field. This is a crucial property for developing low-power quantum electronics. And the field has expanded beyond carbon. The principles of Twistronics apply to any 2D material held together by van der Waals forces. For example, transition metal dichalcogenides, or TMDs, are semiconductors. When you twist bilayers of these materials, you get moire excitons. An exciton is a pairing of an electron and an electron hole. In twisted TMDs, the moire potential traps these excitons in specific spots, creating arrays of single photon emitters. Imagine a grid where each cell can trap and release exactly one photon at a time. This is a holy grail for quantum information technology. Researchers have even observed electrons in twisted TMDs freezing into a solid crystal lattice due to their mutual repulsion, a state of matter called a Wigner crystal, or electron ice. We are also seeing the rise of multilayers. In 2021, researchers discovered that 3 layers of graphene, twisted in a specific sequence, are even more robust superconductors than bilayers. So, where is this all going? What can we actually build with Twistronics? The first major application is likely in quantum computing. Current quantum computers, like Google's Sycamore, use aluminum superconductors. These are fixed, their properties are set during fabrication. A Twistronic qubit could be tuned electrostatically. You could turn the superconductivity on or off, or change its frequency just by changing a gate voltage. This could lead to a voltage-controlled quantum computer, which would be smaller and easier to control. Then, there are smart materials for optics. Twisted graphene interacts strongly with infrared light, while twisted TMDs interact with visible light. We could build super-resolution sensors, or cameras that can switch their sensitivity spectrum instantly. And, of course, there is the dream of room temperature superconductivity. Magic angle graphene itself will likely never reach room temperature. It is too fragile. However, it serves as a simulator. By understanding exactly how the strong correlations in the flat bands create superconductivity, Theorists hope to design new synthetic lattices that replicate that physics at higher temperatures. We are moving toward an era of designer quantum materials. We are no longer limited to the periodic table. We have a third axis of control, the twist angle. This has democratized the study of strongly correlated physics. You don't need a high-pressure diamond anvil or a massive magnet lab. You just need a good microscope, some tape, and a steady hand. The magic of 1.1 degrees was just the first opening of the door. The room behind it is vast, and we have only just stepped inside. Thanks for listening to G Fun Facts Online.